bit of progress in trying to figure out how to put together a decent AI engine. Actually, not even an AI engine, because when you talk about artificial intelligence, it implies that there is some kind of thinking involved. What we're really doing is mechanizing the process, right? So we're mechanizing how word generation works, we're mechanizing how placement works, we are mechanizing how validation works, we're mechanizing how scoring works, right? All of these aspects, when you think about it, when you play against uh, an, an, an engine or a bot or what we call artificial intelligence, when you play Scrabble against it, it feels as if you're playing against something of superior intelligence, but it's essentially a mechanical process operating at a fairly high speed or high frequency. And the combination of mechanics with speed sort of gives you the illusion of intelligence. So how do you actually create that illusion of intelligence? And we're going to try and answer some of those questions and some of those challenges today in today's class. That's the high level game plan. And then once this is done, then there are other pieces where we would come back and look at other aspects of the, is the elegant approach similar to the one that I did? I didn't follow your model. I generated a big index of 5-letter words, and I realized that within that 5-letter index, I'd also generated the indexing for 2 and 4-letter words. So I basically just used one mega index and reference specific columns and translated each row from numbers to letter. That's certainly a better approach, Asad. That's certainly a significantly better approach. I don't know how many of you were there in the Friday tutorial that Usman ran. Usman said something similar, right? He basically said, rather than doing it 2, 3, 4, 5, 6, 7, why don't you just do a single 7-shot combo, and that 7-shot combo would actually have your 1, 2, 3, 4, 5, 6, 7 combinations within it. So it's a smarter approach, it's a better approach than the RR brute force crude approach, but there are even better approaches available, and I think some of those approaches we'll try and discuss today. One objective of computational thinking, and this is something that we discussed in one of our earlier class when we spoke about actor roles and behavior and we spoke about reducing complexity. One objective of trying to get a sense of a better solution is to think in terms of how much storage does the solution require. And storage comes in multiple ways. One is, how much space does it take on your hard disk, but there's a slightly different definition of storage that also looks at how much working memory do we need. So for those of you who have an 8 GB machine or a 16 GB machine, for those of you who are working on the online version of Excel where you were trying to work through Excel on a browser, you would have found that by the time you got to 5, 6 or 7-letter words, you started running into memory challenges and issues. And while your machines were fairly fast with respect to basic, simple Excel sheets, when you started generating 5, 6 or 7-letter sheets, you would find that numbers started to drag, or the speed of the machine started to drag. Some of you also use Power Query. So while we've done Power Query last year, this year we've not done it intentionally. There's a reason for that. We'll talk about that when we meet again in the class. But for even those of you who did Power Query, you find that once you get to 7, 8 or 9 letters, even Power Query starts to lag. I think one of the reasons for that lag is that, again, one would think that having a 16 or a 32 GB machine should be more than enough to address and handle and work through a simple challenge like word generation for Scrabble, but it's not that simple. I think there are significantly larger, difficult, higher challenges that you have to address. And one of the reasons why storage becomes critical and crucial is that despite having 16, and I have I have TAs and students who have 32 GB machines. Despite even having 32 GB machines, you would find that if you approach a problem or approach a challenge using the wrong design, no amount of speed or memory or storage can save you. So I think one requirement when we think in terms of better design or higher design or good design, when you think in terms of putting computational thinking to work, is to figure out a path from higher storage to lower storage, right? What can we do that will allow us to reduce the storage requirement, both in terms of memory as well as on the hard disk? That's one. I think a second challenge is that if you think in terms of search, so pick up that simple statement, validate a word. Now, the dictionary that we're working with, the Collins dictionary, right? The Collins dictionary has roughly, if I remember correctly, about 279,000 words and change. Right? That's the number. Has 279,000 words. Now think about this for a second. Even if the Collins dictionary is sorted, so it goes from A and it goes all the way down to, let's say, the letter Z. And let's say one of the words that we have is ZA. Now you want to validate what ZA is like. So you have 297,000 words and you've got a word that says ZA, right? Now think about this for a second. Every time you have a word that begins with Z, or even let's say XI, a word that begins with X, or even YA or YE or even WE. Think in terms of what it takes to validate these words. So the Collins dictionary has 297,000 words, and the X, the Z's, the Y, the W's are all towards the end. So from a search perspective, what is the most efficient search? Is the most efficient search that every time you see a word that begins with U, Y, X, or Z, should you always start from the top? Or is there a better approach? Now, a better approach could possibly be, you could actually make a statement, or you could actually look at an option where you could take this 297 and split it, right? You can actually break it down. You can index it by the starting letter. So, put all the A's in one row, put all the B's in another row, put all the C's in a third row, and so you have actually 26 rows. And when you have 26 rows, then you would actually have a much faster search, because now what you're going to do is that rather than every time you see A, you just go to the A column. And let's say you have 30,000 words that are of A. Now, normally, if you just use this brute force approach where there was no fine tuning of your search engine or of your search model, you would do the full search. But now, because you have an index of 26 columns that goes from A to Z, and the minute you see Z, rather than starting from here, you actually just jump straight here, which basically means that let's say you have maybe 300 words with Z. So a search for Z no longer requires you to go through 279 or 297,000 words first. It actually just takes you through the first 300, and you can validate that. This is a more efficient search, right? Break it down by the first word or the second word or the third word. All of this from your perspective is essentially adding some level of refinement or some level of intelligence to your calculation. And your primary objective is what? Your primary objective is that, think in terms of a typical Scrabble game. You've gone through the word generation process. So ZA or ZAD or so I don't know how many words. I think there is maybe, if I think about this, maybe about 100 words that come to your mind. So working through the individual challenges of working through and identifying and validating all possible valid combinations of Z based on the tiles that you have and the anchors that you have on the board. Think in terms of how many times do you go back and forth between the dictionary and the board and the rack. So, for a typical slate of 7 tiles, and you think in terms of 2-letter combinations or 3-letter combinations, think in terms of the number of, for every single combination that you try, you'd go back to the dictionary. And when you go back to the dictionary, what do? If you've done the brute force approach, the simple approach, the approach that's sort of there in the original design that you followed, in the brute force approach, despite the fact that you're using VLOOKUP, what's essentially happening is that from your perspective, you start here, then you go all the way down to 297, and that's when you get to Z. If you do this is much faster, much better, but you're still going back and forth again and again and again. So anything that you can do to improve search, anything that you can do to create faster search, will have a huge impact on how fast and how quick your engine works. Because think in terms of how frequently do you do search, how frequently do you do validation. If you think in terms of the sequencing involved in the Scrabble engine, you generate a word, you validate a word, you place a word, you score a word. Now, generation, placement, and validation, in all three of these, you go back to the dictionary and say, is this combination valid? So I've got the original word, and let's say the original word is ZA. But let's also assume that, that A is sitting right on top of a B. So ZA is one word. So there you go, ZA. But then this A is sitting on top of a B. So from a validation perspective, I have to validate two words. I have to validate ZA, and then I also have to validate AB, right? So that's two calls. So in the original word generation, I just have this call, ZA, but when I place the word, I have a second call, which is, AB. So I have two calls. And for each of these two calls, what happens? I go back to the dictionary, I look up the word, I say, is this a valid word? Is the placement valid? And in both instances, I do a full search of the dictionary, and then I come back. So if you can have faster search, your engine's going to be smarter and faster. I think in today's discussion, I think the tools or the elements that we're going to look at today, our primary objective, primary goal is to see what else can we do to make search faster. That the search that we've done so far, the default search engine that we've used, or the default search model that we've used, that search model is not the smartest search model. A smarter search model would not be slow. A faster search model would require at least some level of design or intelligence. And then, if you get to faster search, you're also essentially thinking in terms of what is it that we can do to reduce complexity. So if you remember the discussion that we had in actor roles behavior, one point that we're trying to make is that it's really important, really key for us to do a good job in both understanding, documenting, and designing a solution. It's important that we reduce our focus, we narrow our lens, and focus on the task at hand. So right now, we're not saying Scrabble has many components. We're going to look at all of those components in one go. We're simply saying, let's take one component. Let's say that component is word generation. So word generation then leads to word validation then also leads to word placement leads to word scoring. So I'm not going to look at all four of them together. I'm just going to look at one of them, and that is word generation. And then what can I do to sort of make word generation faster? And that sort of sequences, it breaks down the task, reduces the complexity, reduces the amount of information or data or sequencing or steps or processes that I have to tackle, understand, and design in one go. And whether it's intelligence or whether it's computational thinking, if you can figure out a way to go from a higher storage requirement, both in terms of memory and data, to a lower storage requirement, if you could get to a slower search model to a faster search model, and if you can get from a higher complexity model to a lower complexity model, you would actually have better design. And the whole intent and purpose of teaching you computational thinking, teaching you to think about this, is remember the three principles: elegance, efficiency, effectiveness. I think one of the aspects of, or one of the goals, or one of the keys to sort of solving for faster search, lower complexity, and lower storage is to understand elegancy, efficiency, and effectiveness. And I think some of the things that we'll today will address that directly.